This is my midterm exam rework video. The first problem I will be reworking is problem number 4. It's stated to rewrite the following equation in matrix slash vector form. Specifically, I'll be reworking part B, where I lost 4 of the 5 points on the problem. Problem B, the equation was x1 squared plus x2 squared plus 4x1 minus 3x2 plus 2x1 x2 minus 6 equals 0. This is my original work. And as you can see, I was rushing through the problem and I knew that I didn't have too much time left. So I was kind of just trying to get something down and hope that it was right because I didn't really understand how to rewrite quadratic equations that well and kind of led to a sloppy and wrong solution. So starting out, our goal here is going to be to obviously rewrite the equation in matrix slash vector form. So our first step is going to be to collect and group the terms by degree. So as seen in the equation, we have 3 quadratic terms, x1 squared, x2 squared, and 2x1, x2. 2 linear terms, 4x1, negative 3x2, and 1 constant term, negative 6. Next, we're going to want to rewrite the quadratic terms in matrix slash vector form. First, we're going to write down which quadratic terms we have, which would be x1 squared, x2 squared, and 2x1, x2. Then we're going to represent them using a symmetric matrix. Step 3, represent the linear terms in matrix slash vector form. The linear terms are 4x1 and negative 3x2. As we can see here, we have them represented in vector form. The constant term does not involve x1 or x2, so it'll stay the same. So now we can rewrite equation number 1. This is my final answer for the rework of problem 4. And now I'll move on to the second problem. So I'll also be reworking problem 12. The problem statement stated, the Euler method for simulating the trajectory of a differential equation z dot equals az uses the steps function pseudo inverse of z equals z plus ts az, where the time step is in all of R is the time step. So starting from the initial state z naught, this creates a trajectory as seen right here. Using the matrix exponential, find a way to improve the accuracy of this method. And a hint that was given was, how is the matrix AD equals I plus TSA connected to the matrix exponential? So, I mean, there isn't much to look at with my original work right here. I was cut off by the time constraint and really didn't get to write anything down. I knew how to solve it. I just spent too much time on other problems. So it's unfortunate. I lost 9 out of the 10 points on this problem. And yeah, so let's start with our rework here. So first thing I'd like to do is break down the problem and some important notes before we attempt to solve this. So first thing is that the Euler method gives an approximate solution to a differential equation z dot of t equals a zt. Updating the state z in discrete time steps using equation number 2, which can be rewritten as z of n plus 1 equals I plus time step a times z of n. The time step is TS and A is the matrix. This equation is just an approximation, but not the most accurate one. And that is something that we're going to be focusing on throughout the rest of this problem. The hint suggests that we can find a best approximation, by using the matrix exponential. This pretty much tells us that the original approximation we were given right here is not the best one. So we need to find a better one. So step one, we're going to want to get the matrix exponential into the problem. We want to see like where it fits in. So we can do that by knowing that the exact solution to equation 1, z dot t, is equal to the matrix exponential times z naught, where z naught is the initial state at t equals 0. Next, we want to find a way to improve the Euler method. By looking at equation 2 from above, the term I plus TSA is actually a first order approximation of the exponential. We can check this by looking at the Taylor series expansion of the matrix exponential. As we can see right here, only the first two terms are used for the approximation. This means that AD approximates the matrix exponential, but with very low accuracy. Or maybe not very low, but a lower accuracy than what a better or best approximation might be. To improve the approximation, we can replace AD with a higher order approximation or just use the matrix exponential itself. So now in step 3, we're going to explain the improved accuracy now. So a more accurate or most accurate even step update would be equation 3 here, where z n plus 1 is equal to e to the power of TSA times z n. This equation directly applies the matrix exponential and gives a precise trajectory. Since calculating the matrix exponential exactly is quite unrealistic, we can use a higher order approximation of the Taylor series, such as I plus TSA plus TS squared A squared over 2 factorial plus TS cubed A cubed over 3 factorial, which will greatly improve the accuracy and is computationally feasible. In summary, by using the matrix exponential or a higher order approximation, we can capture more of the dynamics of the system while also reducing the error that comes from using I plus TSA. Thank you.